Can you guys see my screen?
Yeah, we can see it.
Yeah. Okay. So yesterday we went through the ideal transformer and the practical transformer that is not loaded. So we're going to start here. I'm going to present only until 10:10 because Ombalo also has quite a bit to present. So yeah. Okay, so under the research questions for the type 2, I'm reading from my phone, so that's why. So in your own words, why is I2 sometimes called the demagnetizing current? So in order to answer that, I'll just quickly take you through the operation of the practical transformer that's loaded but lossless. Okay, let me zoom in. Yeah. So now, remember this is how our practical transformer with no load looked like. So remember, because we're going step by step, we first start from how we introduce the operation for the ideal. So as usual, V1 sets up an AC current, I0, which sets up a flux that induces E1 and E2, and E2. And then then now, because there's a load here, there's now a voltage across, there's a voltage V2, because now this one is loaded, there's a voltage V2 across the secondary terminals. And then now, okay, so that's here, because of the load characteristics, there's now a current I2 being set up. The I2 being set up, this is now the current in question. So so when I was going through this, I was confused about this direction of I2. I assumed it would go like this, but so just in case there's someone else who might be confused, the reason why I2 is in this direction is because, so first we already had the induced EMF E2, and then now because there's a load, it draws current, so that's why it's in this direction. Higher. Then that current I2 will now, it's not clear, but okay. So I2, so you remember there's a flux set up by I1, by I0 initially. So I2 will now set up another flux. I don't know if you can see. So there's a flux that's opposing the initial flux. And because the flux opposing it, overall, it reduces the total flux. And as it's reducing the total flux, then E1, the back EMF E1 also reduces. But now, in an attempt to restore that imbalance, because now there's an imbalance, the transformer will now draw in an extra current, more current, and that more current should just be enough to offset this disturbance. So it will be I2 prime. So now to answer that question, why is it sometimes called a demagnetizing current? I thought it's just because of the Hall effect, that it sets up a flux which opposes the original flux, which then reduces the overall flux. Yeah. So let's I'm sorry, I'll have to skip all this, but we'll look at the phase diagram because of a certain question. So I'm doing this because of the time. Higher. So in aside from that question, there was a question that he asked us to attempt other questions. So I did one question because all the other questions are almost the same. And this one had like a slight cut twist, so that's why I picked it higher. So that this is Dev page 122, question 2. It says that the primary of a single phase 2200 to 39 volt transformer is connected to 2.2 kilovolts, 50 hertz supply. Determine primary and secondary turns of the if the EMF per turn is 6.286. This is something that is under transformer basics, which Stephanie did. So EMF per turn is equals to E1 over N1, and we're getting the secondary turns. So you just throw in the values, you get the turns. You do the same for the secondary side, you get the number of turns. Then now the other question was that the primary current, we're supposed to get the primary current when the secondary current is 200 amps at 0.8 power factor lagging if the no load current is 5 amps at 0.2 power factor lagging. So first you need to remember that secondary current is I2, no load current is I0. So here we're going to need knowledge of the phase diagram with a lagging load. Because if the current is lagging, then the load. What about the ratio Mr. Kenya used to mention? Will you cover? The turns ratio, Amma? Which ratio? Oh, that one was under transformer basics. But the turns ratio, which is the one that's E2 over E1, which is N2 over N1 is equals to K. I think you're seeing that one. Yeah, that one is under transformer basics, so I wasn't going to cover it here, unfortunately. But okay, I can maybe I can, after this I can side chat to you about it if that's okay, Michael. Is that okay? Michael, is it okay if maybe we discuss about it on the side because it wasn't part of, oh, he left, okay. Wait, let me wait for him to come back higher. So, so the lagging load is an inductive load. Higher will come. So this is the phase diagram. We need knowledge of this phase diagram. And basically, this knowledge will help in all the other phase diagrams. Higher. So, in the original phase diagram for the ideal transformer, if you can remember, I will start with that as like a basis. Higher. So we had V1 and E1, which is at this point it's equal in magnitude, but it's antiphase. We touched on this, Jana. And that's why we said V1 is also negative I1 higher. There's now then E2, which is greater in magnitude because we are assuming turns ratio, which is what Michael is saying, E2 over E1, which is the turns ratio is greater than 1. So that's why here E2, it has a larger magnitude. And at this point, E2 is equals to V2. Then we touch this current here, I0. I remember we talked about this when we're doing the transformer, practical transformer with no load. when now the ion losses have been factored in. So we have I naught, the components are Im and Iw. Higher, now we have that. We already had that before. So now we're being told the load is lagging. Yes, a load lagging means that the current will lag the voltage. So that's why I1 here is lagging V2, because remember E2 is equals to V2. Higher. The other thing we know is that when I was reading the operation, you remember initially when there's no load, the current being drawn by the transformer on the primary side is I naught. When the load is put to offset an imbalance, it needs a current that's equal in magnitude to the current I2, which causes the imbalance, but it's anti-phase. The I2 prime is lagging V1, and you remember V1 and V2 are anti-phase, so that's why we have it here higher. And then now remember that now in the primary side we have I1 is equals to I naught plus I2 prime. Now that's what we have as the current being drawn by the transformer on the primary side. So see, that means that I1's components are I2 and I naught. So how did I get I1? It's because, so if we initially had I naught, we had I2 prime. So you know that whole thing for vectors, if you join the dots here, it helps you get I1. So that's all we need to know for this question. So okay, I'm so sorry, I know it's not clear. Let me try and zoom in further higher. So this is just the same phase diagram as explained there. We've been told that the secondary current is 200 amps at 0.8 power factor. So remember, power factor is cos theta. In this case, we call our angles phi. So if you find the angle, it's 36.87. Remember, I2 is the one over here. So it's telling us that it's lagging V2 by 36.87. But we also remember that we have I2 prime, which is antiphase, meaning the angle between V1 and I2 is also 36.87. Remember that, I think this we did in maths, opposite angles, opposite equals, something like that. Yeah. Then now, which other current do we have? We have no load current. Remember, our no load current is this one. So no load current is 5 amps at 0.2 power factor lagging, meaning we can get the angle, which is 78.46. This lagging, it's lagging V1. So let me try and see. Okay, yeah, maybe it's a bit clearer. Okay, so now that 78.6 is the angle between V1 and I naught. So remember, now we have the angle between V1 and I2 prime, and we have an angle between V1 and I naught. And what are we looking for? We're looking for this I1, which is the primary current. So what's the first thing we can get if we have the angle between here and here and the angle all the way between here and here? It means we can get the angle at which I1 is lagging, and we'll do 78.6.78. That's 78. Yeah, 78.46 minus 36.87. So you get the angle at which I1, which is the primary current, is lagging. And that requires 41.59 degrees. So we have that. Yeah. Give me a sec. Okay, sour. So what else do we know? We know. Oh yeah, so Michael, as I'm doing this question, it sort of covers that turns ratio. Yeah, so we also know that, you remember this turns ratio, it's usually, what did I just do? Oh my God. Hey, you guys have already seen a mistake. Okay, sawa, tuendelee tu. Haya, so turns ratio is usually E2 over E1. I know I've written there E1 over E2, although this is E2, this is E1. I'm so sorry, I didn't see that I had, but the values themselves are correct. This is actually what E2 is, but nimeandika hapa E1, sorry. So it's usually E2 over E1. This was our E2, so E1. So we have the turns ratio 0.1086. And then remember, it's usually E2 over E1 is equal to the turns ratio, N2 over N1 is equal to the turns ratio, and I1 over I2, which is equals to the turns ratio, K. But in this case, now I have to take you through the derivation. Instead of I1 over I2, it's usually I2 prime over I2, and remember I2 prime is on the primary side, I1 is equals to K. So you might be asking, why is it that we don't say, because I1 is I naught, it's both I naught, it has a component of I naught and has a component of I2 prime. So I'm going to quickly take you through the reason why. Give me a second. Yeah, just quickly take you through. So if I can take you back to the fact that I2 in the secondary side creates a disturbance, yeah? So the MMF, the disturbance MMF is N2 times I2. And the flux caused by that disturbance is the MMF, caused the disturbance MMF over reluctance. So you remember these formulas from first sem. Then remember that the flux that's supposed to correct this disturbance is supposed to be equal to it. It's opposing its equal, so it like removes it. So that means then the MMF for the correcting MMF over reluctance is equals to the disturbance MMF over reluctance. Then when you do all that, that means the correcting MMF, since it comes from the primary side, will be N1 times correcting current. And then because the MMFs are the same, then you can equate the MMFs. And you end up having the correcting current is equals to KI2. And what is the correcting current? I2 prime. That's why you can directly relate I2 prime and I2. Hi. So I can continue with my question. So so because of this ratio, we have I2 prime as 21.72 amps. So we have the I2 prime, we have the lagging, the angle at which I1 is lagging. So now it means if you look at that cross section, just that cross section of the phase diagram, you have now, we said this, you remember I2 prime. Yeah, so you remember we got this angle here. Wait. Oh, guys, sorry. When I was telling you that the 41.59 is this angle, it's this angle between I2 prime and I naught, the angle here. I'm so sorry. Yeah, so it's this whole angle. When you look at this and you complete it like this, it's a parallelogram. So what we want is like the diagonal of the parallelogram. The diagonal of the parallelogram is I1, so that's how we're going to get the magnitude. Okay, so I don't have time to now show you, but if you go and search law of cosines and how to get the diagonal of a parallelogram, you're going to get the, what is it called? The equation you're supposed to use. So we'll do I2 prime squared plus I naught squared plus 2 times I2 prime times I naught times cos theta. And our theta, which is this one here, we got it as 41.59. So if you do all that calculation, you get 25.67.
Nyakabi.
There's also an
Nyakabi.
alternative to
Nyakabi.
this. Yes.
There's a question.
Yeah. Yes. Yes. Oh, okay. Nyokabi, please rewind the angle part. Okay. Sorry. I know I made you guys a bit confused. So let me just do that. Yeah. So initially we were told that the secondary current, which is I2, is lagging 0.8 power factor lagging, when we got that angle as 36.87. So we said this is the angle. Then we have, remember, I2 prime is antiphase. And because of the whole opposite angle, opposite angles are equal. So also I2 prime is lagging I1 by 36.87 degrees. Then we were told that the no load current is 0.2 power factor lagging. So that's if you get the angle, which is 78.46 degrees, it's the angle at which I naught, which is the no load current, is lagging I1. So it's this whole angle here. And then, so now when you have those two angles, if you do this whole angle here minus the angle, so the angle between V1 and I naught minus the angle between V1 and I2 prime will give us like a small angle here between I2 prime and I naught. So yes, that's now the angle that is 41.59. Lynn, is that okay? Okay, sawa. Yeah. Yeah, so now there's an alternative method as opposed to using the law of cosines to get a diagonal. And the alternative method, I do not know the logic behind this, so that's why I chose to not use it, is to say that I1 is equals to, so if V and H, I don't think they mean anything, but let's just say IA, IB. So like, let's say IV is equals to I naught cos theta. So basically, the cos components of both I naught and I2 prime, and then this is made up of the sine components of I naught and I2 prime. And then when you get the whole I1 is equals to square root of IV squared plus IH squared, that gives you what I1 is. So I don't know the logic behind it, and that's why I chose to not use it. Then now the next, so now we have the magnitude, which is 25.67 amps, and you have that Kerr angle. The Kerr angle, which was between I2 prime and I naught, helped us to get this magnitude. Higher. So now the next thing, it's asking for the power factor of the primary current. So what we can do, so you remember, I1 squared is equals to I0 squared plus I2 prime squared. And when we have the cos components, then we can just equate them like this. To 25.67 cos theta 1, which is the angle at which it's lagging that we don't know, and we're looking for this power factor, is equals to 5 cos theta 0, cos theta naught 0.2, which is what we're given, 21/72 cos theta 2. Remember, these are the angles at which they are lagging the voltages. Higher, so you now make this subject of formula, you get the power factor. Higher, and then, okay, I'll quickly go through type 3. In type 3, the question that I'll go through asks to elaborate the statement that winding resistance in transformer model makes the voltages load characteristic dependent. So in order to answer that, we'll need to go through at least one of the phase diagrams, but I'll just quickly take you through. So a type 3 practical transformer is one that's now loaded, and then now the winding resistances are considered. So what does that change? Whatever the operation we had in the type 2 carried forward, now what the extra thing we have is that we have resistance. So remember this model from type 2. Now what we're going to add is the resistance on this side, resistance on this side. And remember, this represents the ideal transformer. And over here, we're slowly modeling it and adding the few things, the things that we are going to start considering in order to finally get our actual transformer. Yeah, so now this is what is going to start answering that question. So from here, we can see that V1 is equals to I1 R1 plus, and you remember I1 is the summation of I0 and I2 prime, remember? So V1 is equal to I1 R1 plus E1. So that's how we're going to get E1 is equals to V1 minus I1 R1. And then from here we can see E2 using the KVL. E2 is equals to V2 plus, okay, I2 R2 plus V2. So that's why we have this. I'm going to skip all this so that we can just go straight to the question. Yeah, so I'm going to use, let's say, I've used the lagging one before, so yeah, I'm going to use the phase diagram for a leading load. So this is going to help answer the question that the voltages are load characteristic dependent. Okay, so we have our phase diagram here. As usual, we have our I0 with its components IW and IM. We have our E1. Remember, so for now, we're going to do, okay, E1. Remember, we have V1, which is antiphase. For now, we're going to draw it as a dotted diagram. You'll see why. As a dotted line, you'll see why. And then the E2, just like we said, higher. So first of all, remember, this is a leading load. A leading load, yeah, a leading load. So meaning the I2 leads. Yeah, I2 is leading. So it's on this side. Okay. Yeah, okay. Okay, so remember the equation that this one is important, that E2 is equals to V2 plus I2R2, meaning V2 is equals to E2 minus I2R2. Remember that equation as we do this. Okay. So I2R2, the one you see here, is because it has I2, what's it called? Yeah, it just has it's I2R2, meaning if you were to draw this, it should be parallel. First of all, it should be parallel to I2, and the magnitude will be dependent on on R2. So that's why we have it. First of all, the direction is the same because it's parallel. So see, we have it there. The other thing you remember is that V2 is going to be E2 minus I2R2. And that's what you're going to see here. So you remember we said that I2R2 is facing this direction, meaning going the opposite direction is going to be minus. So E2 minus R2R2 is going to take us to the point where V2 is, and then you draw V2. So that's slowly starting to show you that the voltage is dependent on the voltage dependent on the load characteristic. Oh yeah, does this? Yes. Okay, maybe someone can help me, but I thought that's what would really answer, because you see I2, which is leading, it's leading because of the load, is what is going to result in this, and that's going to affect where V2 is. Yes. So now we're going to go here. Remember, we have now our I2. Remember, we have I2 prime, which is antiphase. And then in order to get I1, we did this before. It's the diagonal to this parallelogram higher. So the reason why we drew the V1 as a dotted line is because it's not actually here. Remember, it's now voltage, it's now load dependent, right? So, oh, okay, no. This is what I think. This part is what fully explains why it's load dependent, because it's on the mini side. Oh no, yeah, actually, okay. So the reason why this could also explain why it's load dependent is because you remember I1 is it's I1 has the component I0 and I2 prime. The reason why we have I2 prime is again because of that load. And so we see that it affects where V1 is, as I said, so this parallel. So the line here should be parallel until the point where this is negative E1. So you draw it parallel until this point. Remember, the magnitude is affected by the value of the resistance. And when you get to that point, then that's what's going to give us V1. So let me just phrase my answer properly. So the reason why I think it's load characteristic dependent is because just from the phasor diagram, we see that the currents, both the current in the secondary and the primary, are affected by that load in one way or another, and that in turn it affects where the V2 is. So V2 is no longer in phase with E2 because of that, and V1 is no longer completely anti-phase with E1 because of that. Okay. So I'm now going to go to, okay, sorry guys. I'm now going to go to type 4. The type 4 transformer is a practical transformer. It's loaded, it has winding resistance, and now we are considering flux leakage. So you'll see this is what is now considered the actual transformer. You remember in the ideal, all this, we were just assuming there are no losses, there's no leakage, there's no resistance. So here, this is the actual transformer. So in the research questions, there's a question that touches on the circuit model. So in order to get the circuit model and quickly go through this, so we know that just whatever we said in the operation of type 3, we're going to carry it forward here, only that now we're adding x1 and x2. And to diagrammatically represent that, in our circuit model, you remember it, we now have the flux leakages are represented by inductance. So we have this for x1, and then we have for the secondary side. So we have flux leakages, the primary and secondary findings. So the question asked why R1 X1 is here, is located to the left, and R is located to the left, yeah, and R0 X0 is located to the right. So when you think about it, we're just going to go back to this equation. So from here, we get the equations E1 is equals to V1 minus. Now it's no longer resistive peke. You remember it would have been I1 R1 in the previous type, but now it's Z1 being equals to this. So if you look at it like this, if this section was located here, because that's what they're asking, it would mean that I1, so okay, no, then okay, no, let me get back to this. Remember, I1 is equals to I0 plus I2 prime, meaning in this case, this impedance, if you open the brackets, you see it would be I0 times the impedance minus I0 minus I2 prime times the impedance. If it was located here, then the impedance would only affect I2 prime, and that's not what we need here for now. So it has to be located here so that this impedance affects the whole current, including I0 and I2 prime. So that's the reason why. Then the other thing, the other one is a question. A question from Sadev.
Nyakabi?
Yeah.
Oh. Okay,
Yeah.
the call has been answered.
Oh. Oh. Okay. Oh, it's been answered. Okay. Okay, so the question is, a 5,500 volts one-phase transformer has primary and secondary resistance of 0.2 ohm and 0.025 ohm, and corresponding reactance of 4 ohm and 0.04 ohm, respectively. Determine equivalent resistance and reactance of primary referred to secondary. So this is a concept that we'll have to go through. And I have it here. I'm sorry, my work is a bit. Wait, sorry guys, give me a moment. What did I include? Oh yeah, I know I included it. Okay, I'm so sorry guys. Forgive me. So I'm going to take you back to a concept. that's here. Okay, so for ease of analysis, what happens is we can bring the resistance that's in we can bring all the resistances on one side just for ease of analysis. So how's that going to affect everything? So if you bring R2 to this side, how are we going to get what the actual value of R2 prime, which is being brought to this side? R2 being brought to this side. Okay, let me just explain. So from what we know about the whole turns ratio, I2 prime squared R is equals to I2 prime squared R2. Why? Because you know I2 prime over I2, you know that turns ratio relation that is why we're doing this. So you make R the subject of the formula because that we're looking for the value of the resistance, the one in the secondary side, the value it would be if you bring it to the primary side. So when you do all this, you get R, that R is equals to R2 over K squared, K being the turns ratio. So it's equals to R2 prime. That's what this R2 prime would be. Then let's see what it would be if we move the resistance in the primary side to the secondary side. And this is what it would be, because I1 squared R1 is supposed to be equal to I2 squared R, and then it will give us K squared R1. So we're going to need that to do the following question. Yeah, so you remember now I've said remember what you did there. Similarly, like it also applies to the reactances, just the same relation. X2 prime would be X2 over K squared and X1 prime would be K squared X1. When you're moving both the resistance and the reactance, then it's called impedance shifting. Because you're shifting, yeah. Yeah. So now, actually, this question, I'll quickly go through it because once you know that, you have the answers. Because here it's asking equivalent resistance and reactance of primary referred to secondary. So that means, sorry guys. So that means we're transferring the reactances and the resistance, so impedance shifting to the secondary side. So I won't take you through it step by step, but you see, because you have the formulas, you'll be able to get the answers. Here it's asking for now the total resistance, reactance referred to the primary and secondary. So here it was just asking about the resistances and reactances referred. Here we're asking about the total. So you also have to add, if it's R1 prime, you also have to add the resistance of the secondary, same to the reactance. So that's what this question is about. I'm sorry, naenda haraka kiasi, but yeah. Once you have those relations, uko sawa. So I think I'll just go through one phase diagram, just because I think it might be important. So we're going to go through the phase diagram for an inductive load. Remember, this is a type 4 transformer where we are now considering reactances also. Let me go through lagging because I went through leading in the previous one, so it will just be, yeah, okay. So as usual, we have our I naught with its components IWM. We have E1 and the antiphase negative E1. Yeah. And then we have E2. Those ones, you know how we get them. Then now we have I2 which is leading. So remember now our voltage is going to be affected by both the resistance and the reactance. So that's how we're going to come here. The way I said, so I2, remember we have I2 R2, which is parallel. So that brings about this. Okay, now maybe, I'm sorry guys, let me just, maybe this would help give a bigger picture. So you remember the formulas are that E2 is equals to V2 plus I2 Z2, meaning V2 is equals to E2 minus I2 Z2. And so you remember this triangle? Yeah, Z with the okay, yani the whole thing for Z is equals to R squared plus X, the resistance squared plus reactance squared square root, yani this triangle. So that's what we need in this, that's what we're using in this phasor diagram. So remember we said V2 is equals to E2 minus Z2. If it's minus Z2, then we're going to put the Z2, which is it's dotted, is going to face in this direction. So that if you're going up, it's going to be minus. And then that's why now with that cut triangle, we have the I2 R2, which is parallel to this I2 R2. And then this component will be I2Z to X2. So that's why we have that. And then you do, it's the same thing for the primary side. So that's why I just wanted to quickly go through that, because now it's an impedance and not just a resistance. Okay, so that's it for type 4. Okay, so the other thing that we need to go through is now, in this one I'll use the slides, is now equivalent transformer circuit. So now we have the type 4 transformer is now our actual transformer. So now we want to start analyzing our actual transformer. And how will we analyze our actual transformer? We need to start simplifying it so that it can be easier for us to analyze it. So you remember this circuit diagram that we had when I was talking about the type 4? Okay. Okay, so how are we going to start simplifying it? So again, here it is. So, oh yeah, the reason why I'm going through this is because in the research question, there's a question that says, write a brief commentary on the equivalent transformer circuit and its simplification process. So yeah, so now here we're talking about the simplification process. Here is the circuit. So the one thing you should know, or the one thing that, yeah, is that I0, you remember here we say the no load current. I0 is usually very small. And when I Googled, it's very small because it's when there's no load, that current is should just be enough to set up the leakage, the flux linkage, the flux, and to cater for ion losses. So it's very small. And because it's small, and you remember initially I was telling you that it like R1 X1 has to be to the left of R0 X0. But okay, so I have 10 more minutes higher. But because it's very, and you remember the reason why I gave is just from that equation, because if you were to, yeah. So, but because it's so small, even if you take it to the left, it won't really make a difference. it won't really make a difference. So you can take it to the left, and then you can just remove it. Sorry. Yeah, because it's really small. And that's how you end up with this simplified form. I hope you guys have understood that. So you remember it's very small. So the way we were saying that, let's say for E1, it would be E1 is equals to V1 minus I1 Z1, and the Z1, the I1, which is I0 plus I2 prime, is multiplied by the impedance, which is the resistance and the reactance. And remember, we're saying the reason why it's on the left is because that resistance and reactance affects both the components. But we're being told it's so small. So anyway, even if it's moved to the right, or if we do away with it, it's fine. So such that instead of I1 being I0 plus I2 prime, then our I1 is equals to our I2 prime. So that's the simplified form. So I've quickly gone through the simplified form. The next question was, the next question is, if I0, which is the no load current, is taken as non-trivial, meaning if it was significant, how is the link chain affected in terms of function dependency? First, I'm going to say what the link chain is. I'm going to touch on what the link chain is. Let me zoom in carefully. Wow. Okay. Oh, shit. Yeah, okay, that's better. So, remember initially this equation, this one for the primary side, V1 is equals to E1 plus I1 times the impedance. And remember, this is just what I was saying. I1 is I0 plus I2 prime. And now we're saying the I0 is trivial. So that's why we remain with I2 prime. So what this helps with is that we can now easily relate, V1 to E1, because, okay, so you remember that I2 prime is equals to K times I2. And you remember why I had said that initially, that the whole MMF disturbance MMF. So because we have this, and from this secondary side equation, if we make I2 the subject of the formula, you get E2 minus V2 over R2 plus JX2. Because we have that, and we have this relation, it means you can even come here, and if you replace here with KI2, and then you replace the I2 with this. So you see, it means when the I0 is not there, honestly, we can easily have the relation between V1 and E2 and, and V1. So we can easily have that. So the question is asking, like, what would happen if I0 is not trivial? If I0 was not trivial, meaning we just have this full form, if you start replacing, you have the I0 component. So it's no longer easy for you to relate like V2, V1 and E2. Yeah, so that's why we need it. That's what would happen if it wasn't trivial. Okay. So in the 5 minutes I have, I will quickly go through the section of this, which is simplified phasor diagram. So see, now we've simplified our transformer, the equivalent transformer diagram. So that means we can simplify our phasor diagrams. Okay, so in this section, there was no question. The reason why I would go through it is because, and I think now you may have to read for yourselves, because there's another section called approximate and exact voltage drops in a transformer. To answer the questions here, you need the background of this section. So even if I was to answer, in order to like explain, you'd need the background information for here. So I think I'll just go through. So we'll just go through it. So you remember now we have our simplified transformer diagram. Here. So if you can remember, I think I can show it. So this is the phasor diagram when we've simplified the equivalent circuit. And you remember, when you simplify the equivalent circuit, it means I naught is 0. So remember, initially, if you had so you remember when I was taking you through the leading one, initially we had the I naught, and I1's component was I naught and I2 prime. So in this, the difference between that and this is that now we don't have I naught, and now I1 is equals to, let me see if I can. So we don't have I naught, and now I1 is equals to I2 prime. And remember, I2 prime is the one that's anti-phase to I2. So that's the difference. So when you're now constructing, let's say when you're constructing V2, it will change. V1, actually, sorry, V1 it will change, because you remember the I1 R1 should be parallel. So that's what changes. Lakini hatujamalizana na simplification. So you remember I was telling you that because now I naught is trivial, we can easily relate V2 with V1, V2 with, you know. So this is how we relate. So you remember turns ratio is here. So E2 over E1 is equals to K, meaning E2 is K E1. This is one of the ways we can relate V2 to V1. That means E2 is equals to KE1. No. Meaning if, and remember we said V2 is equals to KE1. Please give me some time. Wait, I don't know why. Oh yeah, okay, sawa. So we have V1 is equals to E1 plus I1 Z1. We have 1 minute. Okay, meaning E1 is equals to, E1 is equals to V1 minus I1 Z1. So based on this relation, we can multiply this equation by K, and we can replace, because we said it is equals to KE1, we can replace that into the equation. So now we have V2 in terms of V1. So we have V2 is equals to KV1 minus KI Z1, K1 Z1 minus I2 Z2 because of the replacing. Okay, so okay. So let me just take you through this. So what that will, and I think now you'll read. You guys will go through this. I'm sure you have, but so that will help us now mirror. We can now mirror. Remember our phase diagram. We can now mirror everything on the primary side to the secondary side. So that's what it helps with. And then from there, we can, from there you use this to get approximate voltage drop, the actual voltage drop, and then now you continue with your analysis. I'm sorry guys, I'm not able to take you through everything, but I hope the bits that I touched on you understood. If you have any questions and you haven't been able to ask, you can ask me. On the side. Yeah, you can ask me on the side. Okay, so Umbalo, you can present.
Okay, thank you, Nyokabi. First of all, I'm not sure you guys can hear me, so someone please. Can you hear me?
Tunakusikia.
How was it? Okay, so let me just present my screen kwanza. Someone give me a heads up kama unaweza ona screen yangu.
We can see it.
Can you see it now? Okay. All right, so I am supposed to go through transformer tests, which is what we are going to go through. And we are going to have some few calculations, especially for open circuit and short circuit tests. There are 4 tests: open circuit, short circuit, back-to-back and ratio tests, and polarity test. So open circuit and short circuit tests are more intensive than the rest of the 2 because there's a lot of calculations. I try to focus on calculations in open and short circuit tests because that is where I guess that's the juice of it. So we'll start with open circuit tests, and briefly I will just give you the idea of how I want to go through this. So these are the research questions from the PowerPoint document that was sent by Kinyua, and I went through 2 books. I was using Sadev and Taraja mostly. So I went through all these questions, which we are going to answer in a bit, but I left question 7 and question 11 for us to attempt, and then I'll send the results after. Yeah, so for open circuit test, this is going to be a build-up from what Nyokabi has already presented. I will start with going through what an equivalent circuit of a transformer looks like, and we'll go through it pretty quickly because there's plenty of calculations, and I'm not sure we're going to have enough time to go through all of them if we spend a lot of time. So let's dive in. So this is what an equivalent circuit of a transformer looks like. If we have a transformer like this, we can generate an equivalent circuit like this one here. And if you notice, there's 2 parts of the primary side. There's R1, X1, and then there's this part that has R0 and X0 in parallel. So the R1 and X1 represent the copper losses in the primary side, and then the R0 and X0 represent the core losses or the ion losses. The secondary side also has copper losses, which are represented as R2 and X2 here. So Nyokabi had already presented this, and we can join these 2, R1, X1 and R2, X2, to form one circuit. that shows the copper losses. So the total resistances can be put together to form an equivalent resistance, and the reactance is also an equivalent reactance. Depending on whether they'll be on the primary or secondary side, now that's the equivalent reactance or the equivalent resistance. Depending on whether they will be either the primary or the secondary side, we will use R equivalent primary, R equivalent secondary, and X equivalent primary and X equivalent secondary to denote the equivalence on primary can be converted to its equivalent R equivalent secondary using a formula, which is what Nyokabi already went through also. You will see the formula in a bit. All that is in page 1132 of the Raja under equivalence resistance. Okay, so open circuit test. What exactly is an open circuit test? The open circuit test is normally performed on the low voltage side of a transformer. And then the high voltage side of the transformer is left open. So the test is performed on low voltage winding, and the reason for that is because the voltage and the current are inversely proportional from this formula P is equals to IV. So when the test is done on the high voltage side, because the voltage is high, then the current will be very low. And when the current is low, it can't be measured by an ammeter. Also, if we conduct it on the high voltage side, the high voltage cannot be measured by a voltmeter. It will be too high. So that's the reason why the low voltage, the open circuit test is conducted on the low voltage end. Right, so if you have an open circuit diagram like this one, we have an ammeter, we have a voltmeter. The voltmeter is connected across the input terminals of the transformer. This is an external transformer, but this is the transformer on which we are conducting the test on. So this is the input voltage, and this is the input current. Now, if we have on the high voltage end or on the secondary end, if there's an open circuit like this, it means there's pretty much no current flowing. There's really no current flowing on the high voltage side. So it means the demand of the current from this transformer, or the input current, I naught, as we will refer to it, is going to be the current that is going to be utilized or just lost within the transformer, because there's no current that is going to do any job to create another current in the high voltage side. So all that current that is going to be demanded is only going to be current that is going to be utilized in losses in the core. So the current measured by the ammeter, I naught, is also referred as the no load current, is going to be pretty much the current that is going to drive the core losses. The voltage that is across the input is called primary voltage. And then because the high voltage side is open, the power that is measured by the wattmeter is going to translate directly into the core losses. The core losses are also known as the iron losses. So from open circuit test, we have gotten three measurements. We have the voltage, we have the current, and we have the power. We have all agreed that the current is going to be the current that drives the losses in the transformer, and the power measured by the wattmeter is going to directly translate to the core losses. So then, this formula here is something Nyokabi had already gone through, that the power is given by VI cos phi. So in our particular case, because we are working on open circuit test or no load test, the power given by W naught is going to be V naught, I naught, cos phi naught. So from this, we get our first formula. We can get cos phi naught from what we have measured. All these are parameters we have measured in an open circuit test. So wattmeter over the power measured by the wattmeter over what the voltmeter measures times. This is directly from this formula. And cos phi naught is called the null or factor angle. Now, we have already seen what an open circuit tests for. We know that it tests for the core losses or the ion losses in a transformer. So an equivalent circuit that can represent this, we know that every time we have and a transformer or any device, really, we draw an equivalent circuit to enable us to analyze it electrically. So this is an equivalent circuit for what the open circuit tests for. So this is representing the core losses. In the core losses, we have I and X naught. These are the resistance and the reactance here are equivalent circuit that represent what is lost because of the excitation in the core. This is its phasor diagram, right? So from this here, from the phasor diagram here, we have I naught, and the I naught breaks down to form IW and I mag, which is the current because of the magnetic component. We have a magnetic component, so I naught is a factor, has two components, IW and I mu or I mag, which is the magnetic component. Okay, so from this, mathematically, we can get IW, which will be I naught cos phi, and we can also get I mu, which will be I naught sin phi. So these are important because we are going to use them in the calculations that are going to come later on. And then we also have R naught. We can obtain R naught because the voltage across both R naught, we divide it by one of these currents, we will either get R naught or X naught. So R naught here will be V naught over the current through R naught, which is IW. X naught will be again the voltage divided by the current. V naught, the magnetic component, the current of the magnetic component. Yeah, so these are the parameters of the open circuit test. We have the current, I naught, no load current. That's the first component. We have this component that goes through the resistance and this component that goes through the reactance, which is IW and I mu. All these form the current components of an open circuit. And then what else? Yeah, so the open circuit test enables us to find the open circuit parameters. And the open circuit parameters are IW, ion loss component, I mu, magnetizing component. Both of these form the no load current. And then R naught, the exciting resistance, and X naught, the exciting reactance. So these are important because a question can be formed and they can ask us to get the open circuit parameters. So these are what we'll be looking for. And whenever we have a question, we are given what parameters have been measured from the open circuit tests, which is V naught, I naught, and the power. Yeah, so that's the open circuit test, and we will just look at a small question here for the open circuit test. Obtain the equivalent circuit of a transformer with this ratio 200 volts to 400 volts, 50 hertz, one phase, from these parameters that we have been given that have been tested. So on conducting an open circuit test, these are the parameters that we got: 200 volts, 0.7 amperes, and 70 watts. And again, the open circuit test is conducted on the low voltage side. And then the short circuit test is conducted on the high voltage side, as we will see when we get there. But these are the parameters we have from the open circuit test. So from the open circuit test, we know already, we had this formula that the power is given by V I cos phi, right? So we have V because we have been given here, and we have I, which is 0.7, and we don't have cos phi, but we have the power. So this can enable us to get cos phi. So cos phi is 0.5 and sin phi is 0.87. Now the ion loss component is going to be from the phasor diagram. If you guys can remember, the ion loss component is going to be given by I naught cos phi. So we find the ion loss component to be 0.35. And then the magnetizing component is going to be I naught sin phi. This becomes, oops, I didn't do that. So this is how to calculate them. I will send a final document after finding these answers, but it's pretty clear that we can get the magnetizing component, the ion loss component, the magnetizing component, and R naught and X naught as well. So IW, I mu, R naught, and X naught form the open circuit parameters, and from that we can draw what an equivalent circuit of an open circuit test is, and this is it. So if you're asked to draw the equivalent circuit of this open circuit test, it will have these parameters here. R01 and X01 are copper losses. These are unnecessary, but I just did them in this question because it was asking for short circuit test as well. So I just used this example to illustrate open circuit, but we will see what R01 and X01 are when we get to short circuit. Any questions so far? Because next we're going to short circuit test. Anyone with a question? Can you guys still hear me?
Yeah.
Yes.
Okay. Okay, so short circuit test. It's pretty much the same as the open circuit test, except this time round, now the secondary is shorted. The difference between open circuit and short circuit test is the short circuit test is conducted in the high voltage end of the transformer. The open circuit test, if you remember, was conducted on the low voltage end. And the high voltage end and low voltage end can either be the primary or the secondary, depending on whether the transformer is step up or step down. But what important point to remember is short circuit test is conducted on the high voltage end of the transformer. The reasons are the same, just for the constraints of the meters. So if we conduct a short circuit test on the low voltage end, the current is going to be very high, and we cannot measure those currents with the available meters. So normally the short circuit test is performed on high voltage winding while short circuiting the low voltage winding. The readings that are going to be obtained, again, we have a voltmeter, ammeter, and a wattmeter. So short circuit voltage, short circuit current, and short circuit power. the short circuit voltage is very low compared to the rated voltage, right? So the voltage that you're going to measure here is going to be very low compared to the voltage of the supply. I mean the voltage of the transformer, the rating of the transformer has a rating, like the maximum voltage it can take. So the voltage that is going to be supplied here is going to be very low compared to the rating of the transformer. So then the losses that depend on voltage are going to suffer, for lack of a better term. So the losses that depend on the voltage are the core losses. So if we have a very low voltage like we have in a short circuit test, then the core losses are going to be negligible because the voltage is very low and the core losses depend on the voltage. So then what the wattmeter is going to measure is basically going to be the other losses, which are the copper losses, because there's going to be huge current, low voltage, huge current. And we know it's the current that flows through the resistance and the reactance. So the current is going to excite the resistance and the reactance, and so there's going to be copper losses. There's going to be very low ion losses or core losses, next to negligible. So then whatever the wattmeter is going to measure in a short circuit test is going to be assumed to be purely the core losses, the copper losses, I'm sorry. So from short circuit test, we have these three parameters. And because copper losses are also known as I squared R losses, so whatever we're going to get from the reading of the wattmeter in a short circuit test is going to be directly the copper losses, which are the I squared R losses. This is from P is equals to I squared R. So then R is going to be the power divided by the current. And then we can also get Z, which is the impedance. We know V is equals to IR, so, or IZ, sorry. So we can get Z by dividing the voltage with the current. And then we can also get the reactance. Because we have Z and we have R now, we can get the reactance by getting the square root of their squares. Yeah, so these are the parameters that we can get from, or the components that we can get from a short circuit test. We can get the copper losses, which is from the power, and then from the power we can obtain the resistance. This resistance is going to be the equivalent resistance. Let me just explain it once more. Because there are no copper losses, because there are no core losses, whatever the wattmeter is going to measure is going to be purely copper losses, but it is going to be copper losses that include both the primary and the secondary. So when we represent the equivalent circuit of a transformer, when we talk about the R and X components, they're going to be both the primary and the secondary side. Basically, the copper losses in both primary and secondary. So now we know these are important because we are going to be using these components, and a question can ask us to obtain these components from a short circuit test when we are given the parameters measured in the short circuit test. So from both tests, that's the open circuit test and the short circuit test, we can obtain the full equivalent circuit. Because now we have this here, if you remember, represents the losses in the core, and these two represent the losses in the winding of the copper losses. Yeah, so this here just core losses obtained from open circuit test, copper losses obtained from short circuit test. The secondary equivalents, RSE and XSE, can be converted to primary equivalents using this formula. This Nyokabi had already gone through. If we have From the short circuit test, we can obtain RSE and XSE. We can always represent these as their primary equivalents using this formula. And then transformer efficiency is given by this. We will be given the rating of the transformer. So that divided by the same, which is the rating, the power from the rating, and divided by the power from the rating plus the iron losses plus the copper losses. And then transformer regulation is basically the losses that are through the resistor, the copper losses, because this is the loss through the resistor and the loss through the inductor, which is the reactance, divided by E2. So this is the formula that we use to find transformer regulation. So now we've gone through the open circuit test and the short circuit test, and we can start looking at questions. So example 1. A 15 kilovolt 440 230 transformer 50 hertz give the following results. The open circuit is conducted on low voltage 250 1.8. That short circuit, these compute the parameters of the equivalent circuit referred to the low voltage side. So we will conduct an open circuit test, which will give us the parameters of the open circuit tests. If you guys remember them, these are the parameters from the open circuit test. And then we will conduct a short circuit test, but this is going to be on the high voltage side. So you realize this side is the high voltage on our left, but we wanted the parameters on the low voltage side. So after obtaining the parameters on the high voltage side, then we will convert them to their equivalent in the low voltage side. So this is what we expect our equivalent circuit to look like. So now we're just going to look for the parameters. Now these are the parameters we have been given. From the open circuit test, we know power is equals to IV. So to obtain the iron loss component, we are going to take W over V. That gives us this. And from that, we can get the magnetizing component. So we've obtained the magnetizing component and the iron loss component. Now next, we're going to obtain R naught and X naught. R naught V over I. X naught is also going to be V over I, just the respective current, either the magnetizing or the iron component. So now we get both of them, and these here represent the short circuit components. So we have all of them right now, but now we have to obtain the short circuit components as well, R and X. So first we'll start with obtaining Z, because we have been given V and I for the short circuit. That's what we measured. So we can obtain the equivalent of the primary, which is the low voltage, which is the high voltage. Sorry. The primary here is the high voltage. That's why it's Z equivalent of the primary. So Z equivalent of the primary is going to be V that we measured over I that we measured, which gives us this. And R, this is obtained from power is equals to I squared R. So R is going to be power over the square of the current, which gives us this. And from these two, we had this formula, if you guys can remember, so we can get the reactance as well. So now we have the short circuit parameters, but it is on our high voltage side, because short circuit test is conducted on the high voltage side. So we are going to convert these into the secondary equivalent, or the low voltage side equivalent. So first we'll have to obtain the transformer ratio. These we were given because it was a 230 440 transformer. So we obtained the ratio to be this. So the R equivalent, and then yeah, so we obtain the R equivalent according to secondary and X equivalent according to secondary. So once you obtain all these values, you can come back to the equivalent circuit and just plug them in, and that becomes the equivalent circuit. So I guess we've answered that one. Compute the parameters of the equivalent circuit and refer them to the low voltage side. Yeah, so the second example, it's the same. We've been given the rating of the transformer, and then the tests were conducted. We have an open circuit test and a short circuit test. Actually, I didn't want to go through example 2 first, because example 2 is a case where they conducted the short circuit side test we said is conducted on the high voltage side. It can be conducted on the low voltage side, but it's conducted on the high voltage side because of the constraints of the meters. So this is a case where they conducted a short circuit test in the low voltage side. So it's a bit confusing. So I'd want us to go through example 3 first, and perhaps if we get time, we can come back to this one. But it's just the same. So you can go through it later on if we don't find the time, but if we do, we'll come back to it. So example 3. Open circuit test, short circuit tests were conducted on the transformer. We have the parameters for the open circuit test and parameters for short circuit test. The first question says, we draw the equivalent circuit referred to primary, correct? And the second one, calculate the approximate regulation at the transformer at 0.8 power factor lagging and leading. Yeah. So what is new here is the second part. The first part, drawing the equivalent circuit referred to primary. We will just obtain the primary components and then obtain the secondary components. And then depending on whether the short circuit was conducted on primary or secondary. If it's conducted on primary, then well, and it was conducted on secondary, we will have to revert the equivalence of the R and X components to primary, because you want the equivalent circuit as referred to primary. So this is what we expect our equivalent circuit to look like. Now this is going to be obtained through open circuit test. This is obtained through short circuit test. So this is the procedure. We are going to determine open circuit parameters, determine short circuit parameters, and then using conversion formula, determine the equivalence. Yeah. The equivalence of RES, ZES, and XES referring to primary. Because the transformer here is a step-up transformer, we are going to conduct the short circuit test on the secondary, because that's the high voltage side. So we'll have to convert the components of the short circuit test into primary, because you want the equivalent circuit as referred to primary. Yeah, so we have all that. These are just the what we have been given. So the procedure is the same. For open circuit, we will first obtain we first obtain the ion component. The ion component is power is equals to VI. So I is equals to power over V. When we get that, once we have the ion component, from this formula we can get the magnetizing component, and then we can get R naught. R naught is V is equals to IR, the old Ohm's law. So we can get that, and we can get X naught as well. From Ohm's law connected in parallel. So R naught or X naught will just depend on which current. So first is to obtain the currents, and then R naught and X naught are going to be obtained respectively depending on the current. Way we are going to handle when it comes to open circuit. From the short circuit, we have to obtain all the short circuit components. So I squared R, short circuit test is copper losses test, it's I squared R. So obtaining R is going to be power. This is the power measured. We have been given this one. We have also been given this one because it was measured by the ammeter. Although we have these three, because they're on the secondary side, we'll have to convert them to the primary side. So converting them to the primary side, this formula here that has the turns ratio. The turns ratio, we will always be given E1 used the equivalence on the primary side and the reactance on the primary side. So once you obtain the primary components and secondary components, we can come back, plug them in your equivalent circuit, and then we have it. The part that is new is the regulation. So percentage regulation as referred to secondary. Now, if you remember, we gave the formula for regulation as the losses due to copper, you add them and then divide them by E2, and then percentage regulation will just be that multiplied by 100. But I2, sorry, let's just go back to the question for a bit. I2 is going to be divided by the voltage on the secondary, right? Yes, so that gives us I2 as 10. So that is what we use as I2 here. We have the rest of the components because we have already obtained them. So if you plug it in, you find it to be 3.44%. When it's lagging, we add, and when it's leading, it's just the same formula, but we subtract. We subtract the inductance component. So down here, 0.8 power factor when it's leading, we subtract it, and we get a negative. When it's leading, we are always going to get a negative. Yeah, so that's question example 2. Those were examples, so we want to start going through the research questions, and we have 20 minutes because I'm supposed to go up to 11:10. So before we go into the questions, can you guys still hear me? Any questions? Someone please confirm.
We can hear you, Umberto.
All right. So now we can start going through the research questions. I will do question 3, question 5, question 6, and leave question 7 and send the answers tomorrow once we have all tried it out. And please, guys, let's try it out and see if we have any problem. You can reach out. I have already done this, so I can help you out. And the Raja, I will do question 8 and then leave question 11 to us. I haven't gone through this book yet and the questions, but I will go through that and send them as well. Okay, so this is just the same question. You realize the parameters are just given as they were given in the examples, but this time we want to find the efficiency. We have been given an efficiency at a particular output, this 500 volts, and a power factor of 0.8. So if you remember, the formula for efficiency that we gave at the beginning was this. The power at the particular point where the transformer is operating over that power plus the core losses plus the copper losses. So the power at the given parameters, which is 10 and 500, is this. And then now we are going to have to obtain the power losses, the iron losses, Pi, and copper losses. So the copper loss at the given parameters, copper losses, we remember the copper losses are given by the short circuit parameters. We can always obtain the copper losses from short circuit parameters. But when the transformer is operating at a particular output, then the copper losses is going to be a fraction of that. It's not going to be purely WC. WC is the power as read by the wattmeter when we are doing a short circuit test. So it's always going to be a fraction if the transformer is operating at a particular point. And in this case, we have been given a point where the transformer is the current at that particular operating point over the current in the short circuit test, that squared times the power. That gives us the copper losses at a particular point where the transformer is operating. So when you plug that in, you find 69.4. We said the iron losses is directly measured during an open circuit test. W naught has been given because it's one of the parameters that we measure when conducting an open circuit test. So this is given directly. So then when we have all that, we can plug them in and get our efficiency, 95.94. Question 5. Again, you realize the format of the questions is just the same. So open circuit test, short circuit test, and part A, components of no load current. Just different English, but the same thing. So components of no load current is components of the open circuit test. The components of open circuit test, we remember, is IW, I mu,
Ombalo, there's a
which
question.
give I naught. Okay.
Yeah.
Is it wrong if I ignore the KVA and 1,000 in both the numerator? That's totally okay, because it's going to be the same thing. They're going to cancel in the numerator and the denominator. So that was redundant. So to change it to VA. So we can assume it both in the numerator and denominator, and we will still get the same thing. Michael, was that your question? Okay. All right. Yeah, so question 5. We will calculate the components of the no load current, and then efficiency and regulation at full load, and power factor of 0.8 lagging. Yeah, so this is familiar to all of us now because it is similar to the previous example. These are now just the parameters we've been given. Considering an open circuit test, again, this procedure. We first obtain the iron magnetizing component, and then we can get R from V is equals to IR. It's just V is going to be the same, which is V2. It's just going to depend on which right, components. On full load current, remember this is the formula for getting the power, the copper loss, the power lost due to copper losses. It's this fraction times what is read by the wattmeter. So now we have to obtain the current at full load. So current at full load, we have been told that the transformer is operating at 5 kVA. So 5 times 1,000 divided by the current in the input. So divided by the current at short circuit, all that squared. If you multiply by the what the wattmeter reads at short circuit test, we get the copper losses at that particular point. Remember, this formula here is used when calculating the at a particular operating point. So first you obtain the current at that operating point. In this case, it was full load. So we use the rating of the transformer to get the current. And then now we multiply it by what the wattmeter read during the short circuit test. So once you obtain that, PI will always remain the same. It never changes because the copper losses, the core losses never change. The copper losses will change depending on the amount of current that is flowing on the windings, but the iron losses will always remain the same, provided the transformer is operating. So PI will directly be what is read during the open circuit test. So since we have all these, we can plug them in and get the efficiency of the transformer to be 97.56. The regulation. Okay, so I had a bit of a problem here because the formula we gave for regulation was a different one, but it is still the same thing if you look at it keenly, because in this case, E2, if you subtract V2, it's going to be the voltage between the copper loss component or the short circuit components. E2 minus V2 divided by E2. So E2 minus V2 is going to be the voltage between the short circuit components, and then we divide that by E2. It's still the same thing as what we did here, but using a different formula. It's just this one here. This is the voltage due to the resistance, and this is the voltage due to the inductance. So this is still the voltage due to the short circuit components divided by E2. So it's the same thing. So going back to our question, where is it? Yeah, this one here. So to find, or we can also get it by V1 minus E1 over V1. So to find V1 over minus E1, we have calculated for the equivalent resistance according to primary, because now we are working with ones, we are referring to the primary. And we also have the reactance according to the primary. So we can find Z, which is the impedance, because we have the resistance and the reactance. And then we have these, so we have calculated for them already. So this is the same formula as this one. This one here is the same formula as this one. And then this one is the same formula as this one. So this is the formula that we are familiar with. So plugging it in, we have I1. I1 we obtain from the rating of the transformer divided by the voltage of the input side. So once you obtain the current I1, we have the rest of the components that we have already obtained. We just plug them in and we can get the regulation. Percentage regulation is this multiplied by 100. So this formula here, E2 minus V2 over E2 is what is given in the book, because I didn't understand what voltage regulation really means. But let's see, voltage regulation is the measure of how well a transformer can maintain constant secondary voltage given a constant primary voltage and wide variance in load current. So this is the formula that is given in the book. So it's safer to use this one, but I tried using the same on the primary and it was giving the same answer. So depending on the parameters that you will have, you can choose to use this one. This one, take it with a grain of salt. So this first one is what we're going to be using. So once you use the first one, you get 3.13. If you use the second one, you're also going to get 3. The definition here tells us, talks about the secondary voltage closer to zero, most voltage. So I didn't exactly get my head around what voltage regulation means. Perhaps if someone understands it, he can explain to us. But the formula is this one here, and it can enable us to get the regulation. Question 6. Oh, question 6 also. Question 6 is on page 1166 of Theraja. It's a simple one because we have been given. Let me see, where was it? We have been given the resistance in percentage. They said it was 15% and the reactance in percentage. So approximate voltage is regulation at, we were supposed to calculate the regulation at unity and at unity power factor at 0.8 power factor lagging and at 0.8 power factor leading. They should have been leading. So when it's leading, we said it's minus. When it's lagging, we said it's plus. So this is on page 11. The research questions that were given for SADEV. So for Theraja, the format of the questions is still the same. We are given the open circuit test parameters, the short circuit test parameters. Compute the parameters of the approximate equivalent circuit referred to the low voltage side and draw the circuit. Again, they have specified that the equivalent circuit is to be referred to the low voltage side. So when conducting a short circuit test, we're going to obtain the short circuit parameters, but using the formula, we'll have to convert them to their equivalents in the low voltage side. So this is what the equivalent circuit will look like. We can't obtain RES and XES directly. We have to obtain them from the high voltage side, which is the primary side, and then convert them. So the same procedure. I want to go through it because of time. From open circuit test, you realize the procedure is just the same. So these are the parameters we have been given. To find the iron loss component, it's going to be the power over the voltage. From that, we can get the magnetizing component. We can get the exciting resistance from V is equals to IR. The exciting reactance from V is equals to IR again, but this time around we use the magnetizing current. And then from short circuit test, we can obtain Z from V is equals to IR. And then if we have Z, we know that the short circuit test is what gives us the copper losses or I squared R losses. So we can obtain R from the power divided by the square of the current. This is the current measured during this short circuit test. So once you have Z and R using this formula, we can obtain X. But since we have the short circuit parameters or short circuit components, sorry, since we have the since we have the short circuit components in primary, and we were supposed to obtain the equivalent circuit in secondary, because secondary was the low voltage side, we convert them using the formula. So now we find RES, the equivalent resistance in the secondary, and equivalent reactance in the secondary. Once we have those, then we can draw the circuit. Yeah, so it will just be plugging in the values that we have found here. Yeah, so the open circuit, that marks the end of the questions. Just a second. So the questions for open circuit and short circuit test, both in SADEV and Raja, were the same, because open circuit test and short circuit test were basically testing on the same thing. So they were the same questions. We have gone through all the three here. Question 7 is left for you to try. I will send the answers. And we have gone through the Raja question, also question 8. So I will send question 11. So the other two tests, the remaining two tests need back-to-back test na polarity test. So we will look at the questions that were given for back-to-back and polarity test and see if we can go through them in the remaining time. We have 3 minutes. I will try and do it in the shortest time possible. I promise not to go past 11:15. So who was this? How did he contribute to making this slide problematic? Okay. This is the guy who invented this test, and the test is also called the Sampner test. This one here is amongst the documents that he'd sent us in the classroom. So I will leave this one for you guys to read, and part 3 as well, because it touches on the document. What parameters is Sampner's test? Sampner's test is the back-to-back test used to determine why is full load testing difficult in large transformers. So question 4 and question 5 are relevant. I guess these are questions that he can choose to ask in exams. So we will go through these two questions: what the test is used to determine, and why full load testing is difficult in large transformers. And I figured those are directly picked up from this book, SADEV, sorry, just a second. The back-to-back test. Yeah, so this is the back-to-back test. It's like a very short read you guys have to do. The question that we want to tackle right now is why is full load testing difficult in large transformers, and what parameters is Sampner's test used to determine? Part 4 and part 5. Okay, so a suitable load, if you get to this point here where my cursor is, a suitable load to absorb full load power of a large transformer may not be easily available. This is why a full load test is hard to do with either open circuit and short circuit test. So it will also be very expensive, as a large amount of energy will be wasted in the load during the test. So I guess that answers question 5. And the parameters that this test tests for are also given here in this document. The voltmeter, yeah, here they are. towards the last part. The ammeter gives the total no load current of the two transformers. The wattmeter gives the full load copper losses of the two transformers. So the wattmeter, the ammeter, and the voltmeter is also given. Where is it? So basically what I'm trying to say is this is a very short read. So because of time, I guess for the two remaining tests, oops. For the two remaining tests, the back-to-back test and the polarity test, the research questions were just word questions. So I didn't spend much of time looking at them, but I figured they are directly just pulled up from SADIV. Right, so I will send this document to the group. I know because of time, perhaps you guys might not want to ask questions, but you're welcome to ask any questions directly, or you can post them on the group. Or the open and short circuit tests are, I feel like these are the two tests that he's going to majorly focus on because they are calculation questions. For the remaining questions, they are words. And if you guys remember, they had said they're not going to focus on definitions and all because now we have open exams, open book exams. Yeah, so that's a wrap for me. Any questions or any contributions? Oh, I'm just seeing the charts right now. And Alvin is saying in the denominator, it's addition. Oh, right. Yeah, that is right. So Michael, you can't cancel the same component in the numerator and the denominator of let me just go back to it. I remember thinking about it while going through it. So when you're calculating efficiency using this formula, Michael's question was, can we just cancel this part and this one here because they're the same? But since there's an addition here, we cannot just cancel them like that. It will give a totally different answer. As in, this is not equal to 1 over pi plus pc because you can't cancel these two. There's an addition in the denominator. So it will change the whole meaning once we cancel the two. Sorry about that, Michael. And thank you, Alvin, for the clarification. Thank you. You're very welcome. Over to you, Fiona Rugisheru.
Oh, okay. Thank you so much, Ombalo. So I'm sorry, guys, that I was not able to finish the whole of topic 3 in the time that I had. But like I said, I'll compile the questions properly because in the document I had, it was just a mixture. So I'll compile them properly, everything, and send them by Sunday. If you have any questions, just remember you can write on the group. So that's it for, and thank you guys for telling us. Okay, karibuni. So thank you for telling me, thank you. Okay. And okay, so the meeting is now over. I'm going to stop recording. And we are meeting on Sunday.